Alright, what this practice worksheet wants us to do now is find the length of a chord that is contained by an 80-degree arc in a circle with a 4-centimeter radius. So let's just put the basics in that we know already. There's a circle with a 4-centimeter radius. If I want to find the length of a chord that's contained by an 80-degree arc, the first thing I need is an 80-degree arc. So the easiest way to get an arc of what you want is to make a central angle that measures 80 degrees. Now if I drop straight down right here, that central angle looks like it's about 90 degrees. So why don't you draw in with a straight edge a central angle that's about 80 degrees. You don't have to measure it, but there, 80 degrees. There is a central angle because the vertex of that angle is the center of the circle, which means that this arc right here, if I called this point A and this point B, the measure of arc AB is 80 degrees because the central angle is the same measure of the arc that's contained by it. But they want the length of the chord that's contained by it, and a chord is a segment whose endpoints are on the circle. So this green thing right here is like chord AB, and that green chord is completely contained by that 80-degree arc, so they want us to find the length of that. Well, what we can do is realize that this segment right here should also be 4 centimeters because it's a radius of that circle, and I have a triangle in this picture. This triangle is isosceles. It is not a fancy triangle, though. It's not a 45-45-90 or a 30-60-90, so we will not do anything super special. But I can't do Pythagorean theorem to figure out this green side because this is not a right triangle right now. What I want to do, since it's isosceles though, something that's going to help us out a lot is if I dropped in the altitude. Now the altitude will go from the vertex, and the vertex of this is where the two sides of the same touch. So if I drop that altitude in right here and make sure I put this little right angle box, that altitude perpendicularly bisected this green segment right here, and it also bisected this angle to where now that's 40 degrees and 40 degrees. So what I'm looking for is the length of this green side. If I found this X right here, do you see we have just a little bitty right triangle now here, kind of highlighted in blue? If I could find X, since this altitude perpendicularly bisected the green segment, if I found X, all I'd have to do is double that. So to be able to find X, I can't do Pythagorean theorem in this little right triangle because I don't know this side, I don't know that side, but I do know this side. But I can do trigonometry since I know an angle measure and a side length. So we'll use our friend SOHCAHTOA to help us out here and focusing all of our attention around that 40-degree angle. X is opposite it. 4 is adjacent to 40 degree. I'm sorry. Let's say that again. X is opposite the 40-degree angle. 4 is the hypotenuse. So that means we want to use the sine function since we have opposite and hypotenuse. So the sine of the angle measure will equal opposite over hypotenuse, x over 4. Hold on, this thing's being funny real quick. Okay, so I'm back, and this thing is being very funny. Pause one more time real quick. What is going on here? I can't even get it to pause. Okay, sorry about that. Hopefully we're back and I got that problem fixed. But we just used the trig function sine of 40 equals x over 4. So now I'm going to go to my calculator and figure out what x is. So I just need to take 4 times the sine of 40 to do that. And I'll get this. Now that's what x is. Okay. We really don't care what x is. Remember, we want to know what twice the amount of x is because that's only half our answer. So if I go back to my calculator real quick, I'll just take this dirty old number times 2, and there's the length of my chord, approximately 5.1. So what we're going to write down, though, is x was about 2.6 if I did round that to the nearest tenth, but I really didn't care about that. The chord is about 5.1 centimeters. This is the answer that I'm looking for. Excuse me. But I do want to say about how much x was, because some people always put x is about 5.1 centimeters. X isn't. X is about 2.6. But if you double 2.6, you get 5.2. Realize that's really not the right answer, about 5.1. So even though we rounded this answer, we really didn't use it. So the chord was about 5.1 centimeters. Let's try that again. Let's draw in the 12 centimeter radius that we have right here. Excuse me. And I need a 90-degree arc, so that means I'll go straight down and make a central angle of 90 degrees. So that's nice. And that's going to be 12 centimeters again. And I want the chord that's contained by that. So let me get my straight edge, draw in this green chord here. And the whole point of being able to find this missing length is to get a right triangle in our picture. The thing is, I already have a right triangle. You know, I don't need to drop an altitude in. And since I have a right triangle, do you also notice that it's isosceles, since these two sides are the same, meaning this is a 45, 45, 90 right triangle. I know the leg, so the hypotenuse will be the square root of 2 times that. So 12 square roots of 2 centimeters is how long that chord was. I gave an exact answer because I ended up with a 45, 45, 90 right triangle. So the same rules from last chapter apply. If you have a 30, 60, 90, or 45, 45, 90, we'll give exact answers. So let's check this out. 154 degree arc, 9 centimeter radius. So I'll draw in a radius. 154 degree arc, so I want to make 154 degree central angle, so approximately like so. And then I will draw in the chord. Put all my info in. 9, 9, 154. And this is not a special triangle at all. It's not a 90 at all. So I want to drop in the altitude of it. Since it is isosceles, when I drop that altitude in, it perpendicularly bisects the red segment, and it bisects that vertex angle to where that's 77 and 77 now. And if I found x, by focusing my attention and realize I have opposite and hypotenuse. So the sine of 77 will equal x over 9. And I'll just go punch that in. 9 times the sine of 77. And I'll get that, about 8.8. But that's only what x is. I need to take that times 2. So about 17.5 is what my chord is. So x was about 8.8, but the chord is about 17.5 centimeters. Realize we rounded this but didn't use the rounded number. We used the dirty number from our calculator. Excuse me. So this was not a fancy situation because we didn't have a 30, 60, 90 or 45, 45, 90 right triangle again. What do you say we try this one now? 8 centimeters, 60 degrees. So 8, 8, 60, draw the chord in a new color, red chord. What you could do is I'd let you try this on your own and you'd probably get it right. But watch this. Let's make this really, really easy. This is an isosceles triangle that's 60 degrees. These two angles have to be the same because these are the base angles. So since there's 120 degrees left over, and these two angles have to be the same, that means this is 60 degrees, and this is 60 degrees. Ooh, 60, 60, 60, meaning all three angles are the same. That's an equilateral triangle, so that's 8 centimeters. Booyah. I didn't even have to do anything. Or if you'd have went through all the work, you could have done this. You'd have said, okay, well, I got that 60. Let me drop an altitude in. Booyah. That altitude perpendicularly bisects the base, and this should be 30 degrees. This should be 30 degrees. Ooh, if that's 30 degrees and that's 90 degrees, that's 60 degrees. This little green thing is a 30, 60, 90 right triangle. I have the hypotenuse. I'm looking for the short leg. Divide by 2, the short leg is 4. Take it times 2, and that thing was 8 centimeters. So regardless if you did it the short way or the long way, you should have got an exact answer. And you didn't need any trigonometry because 30 degrees was a special number, 30, 60, 90 right triangle. If we go again, 120 degrees. is that a special number or not? Well, let's find out. I'll draw in the situation. 120 degrees does something like that. 6, 6. I need my chord, which is blue this time. This is 120 degrees. This is nothing fancy. It's not a 45, 45, 90 right triangle nor 30, 60 right now. So I will realize it's isosceles and drop this altitude in, which when I do that, this 120 degree angle now became two 60s, a 60 and a 60, which means, ooh, if that's 60 and that's 90, this is 30 degrees. I want to find the x right here, which is the long leg of this. First I need the short leg, so I'll take the hypotenuse and divide it by 2 and get 3. Then that means the long leg is the radical 3 times that. So this guy is 3 radical 3, meaning I need to take that times 2 and realize that's 6 square roots of 3 centimeters is how long that blue chord is right there. So we've gotten exact answers when the arc that they're talking about is 120 degrees, 60 degrees, or 90 degrees. Those are the 3 problems that we've done so far. Does everyone notice that that's this number, 120 times 2, 120 divided by 2 is 60, 60 divided by 2 is 30 degrees, 90 divided by 2 is 45 degrees. These green numbers are the special numbers this chapter. They're twice our special numbers last chapter. Remember, 30, 60, and 90 was a special right triangle because we had rules. And 45, 45, 90 was a special. So the blue numbers are our special numbers right here from last chapter, but this chapter they're twice as much is because we're always dropping in this altitude to split it up. 120 degrees split up 2 equal ways is 60 degrees. We just didn't do that on the other triangles because, when we had that 60 degree angle right here, the whole mamma jamma was equilateral, so we didn't have to do that. But if I did do it, didn't I split the 60 up and get a 30 degree angle? Back here, the 90 degree angle, I didn't drop an altitude in because it already was a 45, 45, 90. But if I really wanted to drop that altitude in, that would now be a 45, 45, 90, just this little guy. So realize there are 3 special numbers this chapter, 60, 120, and 90. If any of those numbers show up, we'll get an exact answer. The last problem they want here is a 43 degree arc, so I'll draw that in. 43 degrees. That's not a special number. 3 centimeter radius, 3 centimeter radius. I want this red chord right here. So I need to drop in an altitude. When I do that, that makes this 21.5 degrees and 21.5 degrees. It's fine to leave that a decimal because I know I'm going to get a decimal for an answer anyway. It's not a special number. It's not 60, 120, or 90. So if I want to find x, I'll do the sine of 21.5 equals opposite over hypotenuse. Punch it in. 3 times the sine of 21.5 is that. I need to round that to 1.1 for x, but that's really not what I'm looking for. I'm looking for this, which is about 2.2. So x was about 1.1, and the chord itself was about 2.2. So weirdo numbers will get approximate answers with a label on it, of course. 30 degrees, not a special number this chapter. It's 60, 120, and 45. Today's new lesson is about how far a person could see. How far could a person see? If we went outside right now, how far could you see? Every person can see to the same point. It's a little different for each person, but the idea is the same. Is if I went outside right now and stood on the ground, I could only see so far. But would you believe that if I stood on top of the building of Hayes High School, that I could see a little bit further? Does that make sense? And obviously, if I got up in a helicopter or something, I could see a lot further than if I could see when I was on top of the building. That's because the higher you are above the Earth's surface, the further you can see. So let's pretend here's me, and then this is how high I am above the Earth's surface. This circle right here is the Earth. So Earth. And how high could, or how far could I see? Well, I could see this far. Because the Earth is not flat, well, Christopher Columbus was wrong. Since the Earth is not flat, it curves off, and if I was really looking, I could see to this point right here. And draw a dot here. This one point right here is how far I could see, and if I continued my sight path in a dotted formation, none of this stuff right here, I couldn't see any of the dotted information because the Earth has like gotten out of my line of sight kind of deal. So the question is, what is this one point called right here? Well, mathematically, that's a point of tangency. That's where this one line that I have has touched the circle. That's a point of tangency, but in our real world, that's called the horizon. Everyone can see to the horizon. It just so happens that the further up in the air you get, the more you can see. Now, it doesn't mean it's like you can see things for super detail. Like if I got up in an airplane right now, I could probably see Waukene, which is 33 miles away, but I'm not reading the T-shirts of people walking the streets in Waukene. What I'm seeing is a bunch of trees and maybe some tall buildings in Waukene, but it's like I could make that out. It's like, hey, over there, look, that's Waukene. There's Waukene over there. I can see information that lets me know that that's Waukene. So if you would hand out this worksheet for them real quick, maybe give them a little pause on the video here so they can all get a worksheet, and then we'll go through it. All right, so the first problem says in the instructions, assume that the radius of the Earth is 3,960 miles or 637 kilometers to do the following problem. So miles and kilometers, depending on what the problem is all about. We need our geometer for all of these problems because we're going to draw some circles. It says, Rita's on vacation with her cats in Paris. She got lucky on her tour of the Eiffel Tower and got to go to the very top, which is 986 feet above the Earth's surface. How far can Rita see? So that's what all today's problems are about, is how far can we see from this point. What we need is a picture here. So let's go ahead and draw a circle and put a center in that circle, and we'll let that circle represent the Earth in two-dimensional space. And make sure you got a little bit of room above your circle to put some stuff, okay? Because what we want to do is we want to say that we're on the Eiffel Tower, which is 986 feet above the Earth's surface. Just put a little segment like right here, and we'll call that 986 feet. That's our Eiffel Tower. I don't need a fancy picture of the Eiffel Tower or anything, but that's saying that we're that far above the Earth's surface. How far could Rita see from there? Well, we'll draw that in. I'll draw in my line right now and just go to where it touches the circle in one spot. That's how far she could see. The question is, how do we solve this problem? Well, what we need is we need a right triangle to do these problems. And the first thing we need to realize is this shape right here is not a triangle because it's got this curve in it. Okay, so the shape that we have on our little Earth right now is not a triangle. What we need to do to create a triangle is, first thing is we need to draw a radius of this circle in. And drawing a radius in anywhere isn't going to help. See, this green thing right here will not help me form a circle. So what do you say we drew a radius from here to here? That's going to help us form a triangle. And I will also draw another radius connecting from the center of the circle to like the bottom of my Eiffel Tower idea right there. There I have a triangle drawn now. What we need to realize is what kind of triangle it is. Is it not true that this point right here, the horizon, is also a point of tangency? And when you have a radius that touches the point of tangency, remember that that angle right there will always be 90 degrees. So we actually have a right triangle in this picture. And we do know some lengths. They tell me the radius of the Earth, but they give me two numbers. They give me miles and they give me kilometers. And the problem is we're in feet over here. So which one would be a better choice, the one that's in miles or the one that's in kilometers? Well, we want to use the one that's in the same system. Isn't miles in the same system as feet? Because that's our standard system right here. This is the metric system. That's not the metric system. So you want to pick the number that's in the same system. So we need this number right here, 3,960 miles. But since this little red distance here is in feet, we would like to make the radius of the Earth in feet. So if we take this number times how many feet there are in a mile, which hopefully you knew that there's 5,280 feet in a mile, we'll realize how long the radius of the Earth is in feet. So take 3,960 times 5,280 and get 2090880 feet is how long the radius of the Earth is. Don't forget commas. Isn't it also true that this little bitty green, or this little distance right here is also a radius, so that's 2090880. And what we have here is we have a right triangle, and we do know this entire side length over here is those two added together, so that's 2090880 plus 986, which is 20909,786, comma. Cool. We have a right triangle. We know two sides. We're looking for this side. We can use the Pythagorean theorem to figure that out. And what we're going to do is I'm finally going to let you get away with not showing a lot of work when it comes to Pythagorean theorem, because these numbers are huge. But the first thing we got to realize is which one's the hypotenuse. Isn't this guy the hypotenuse, because it's across from the 90? And I want you to write down the formula that we're going to use here. So the two legs squared add together to equal the hypotenuse squared. So we're going to write 2090880 squared plus x squared should equal 20909,786 squared with commas. We got to write that down. All right. Now, what we're going to do is we're going to do basically the rest of this in our calculator. Okay, but before I go through with these large numbers, let me go through a very basic one that we should know how to do already. All right, wouldn't it be true that you would square both of these numbers first? And then the next thing you'd do is you'd subtract that thing over, right? Because this guy is bigger. This is the hypotenuse. It's always the biggest side. Well, that's all we got to do here. Let's go ahead and punch this guy in first, since it's the bigger number, into our calculator. It's that 20909,786. Let's punch that in, and we'll square it. And then we're going to have to subtract that other big old number away, so minus 2090880 squared. We'll get that. Is that okay? What we got typed in. And then hit equals. And that's a very, very, very large number. It's in scientific notation. But this isn't our answer. This is what x squared equals. What we got to do to this number to figure out what x equals is square root it. So that's when we use that A and S button. We're going to square root that previous answer, and we'll get that. That is a much nicer number to deal with. And what we're going to do on our sheet is we're going to keep this number dirty in our calculator, but I'm going to go ahead and just round this to the nearest whole number. The question is, what label are we in right now? Well, didn't we change everything to feet? So we could say x is about 203,059 feet. That's how far Rita could see from the top of the Eiffel Tower. But, you know, over 200,000 feet, that's a long, 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 long ways. When we get into that kind of distance, we like to really change it into miles. It's like, how far can you see? How far can you see? I can see 8 million feet. It's like, that doesn't mean anything to me. So what do you say we change this number into miles by keeping it dirty and dividing it by how many feet are in a mile? 5,280. And we get that, and we'll round that number to the nearest tenth. because that's more of a final answer and it's a smaller number. So couldn't she see about 38.5 miles? So she could see about 38.5 miles. I do want to see both answers, how far she could see in feet, and then change that into miles, rounded to the nearest tenth. Alright, so let's try that again. You're going to need this picture to get started. Why don't you go ahead and draw this picture on all three of the remaining problems real quick. So if you want to pause the video and give them time to draw those pictures. So here we go. When Doug was trapped on the roof of Caesar's Palace, he had a great view of Las Vegas. If he was 125 feet above the earth, how far could Doug see? So let's put the 125 in the picture. He's 125 feet above the Earth's surface. So that goes right here. Put labels with it. It helps. How far could Doug see? That's this guy right here. So we don't know that. And we need to put in the radius of the Earth. Since they tell me how high Doug is in feet, we need his the radius in feet using the one in miles. So that's the same old number, that 209,088,00 feet, and this is 209,088,00 feet, and you just got to figure out how long this bad boy is, which would be 209,08925. And now we'll set up our Pythagorean theorem. Please put a right angle box in there also. My picture doesn't have that, but you do need that. And then we'll do the Pythagorean theorem. Write it down, 209,088,00 squared plus x squared equals 209,08925 squared. And we want to do a subtraction because we want to get x squared all by itself. So the bigger number minus the smaller number. So 209,08925 squared minus 209,088,00 squared equals that. Don't care about that. I won't, because that's what x squared equals. We need to square root that number and get about that. So I'll write that down to the nearest whole number. That's x was about 72,299. That label is in feet right now. Then I'm going to change that into miles. So divide that number by 5,280. And yeah, Doug could see about 13.7 miles. 13.7 miles. Now, again, realize, if you're standing on top of Caesar's Palace, you can see about 13.7 miles. Remember, you're not picking up a lot of fine detail of stuff that's 13.7 miles away. You could see that far. That's when the Earth starts to fall off out of your line of vision. So you're seeing some rocks and this is the horizon, but you're not reading somebody's T-shirt from that far away. All right, that should make sense also with the previous answer. Like, Rita could see a lot further from the top of the Eiffel Tower than Doug could when he was on top of Caesar's Palace. And the reason why is the Eiffel Tower is further above the Earth's surface than Caesar's Palace. So should make a little bit of sense. What do you say? You draw that picture and you put the numbers in the right place. So see if you can get it set up. Not every problem is the same. So when standing at the roof of Hayes High, Mr. Harris can see 11,200 meters. He can see that far. And where we can see is always this tangent line basically right here where that's 90 degrees. And so the 11,200 goes right here. How far above the earth is Mr. Harris's eyes? Well, there's a couple ways to do this problem. There's an easy way and there's a hard way. I'd like to show you the easy way. First thing we got to realize is since he can see that far in meters, we want the radius of the earth in meters. 6,375 kilometers is the radius of the earth. Kilo means 1,000, so there's 1,000 meters in a kilometer, and that means that to change that into kilometers, you just multiply, or change it to meters, you multiply that by 1,000, which means you add 3 zeros to it, ladies and gentlemen. So that's how many meters. That's how many meters. What we're going to do to keep this easy is we're going to say, let's just find this side length. Let's call it x. This will be the easy way to do this. So isn't x the hypotenuse since it's across from the 90? So when we set up our Pythagorean theorem, we'll do 11,200 squared plus 6375000 squared equals x squared. And now you realize you don't subtract those two numbers, you add them together. So 11,200 squared plus 6375000 squared equals this number. That's what x squared equals. So I need to square root that thing and get that number. Now, let me go back to my picture here real quick. That's this entire hypotenuse right here, which we really don't need that. All we need is how high is Mr. Harris off the ground. So don't I want to take this entire green length, which is in my calculator, and subtract away the radius of the Earth, which is 6375000. We just want to get rid of that part because we don't care about it. So let's use that dirty old number and just subtract away the radius of the Earth, which was 6375000. And that is really what we're looking for. And we'll round that to the nearest tenth. Mr. Harris is about 9.8 meters. So x is about 9.8 meters above the Earth. And there's no need to change that to kilometers because this answer makes sense. He's not that high, so we'll just measure it in meters. Sweet. One more. First thing we got to do, though, is I made a typo. There shouldn't be a 5 there. It's just to the nearest meter, how far above the Earth is a plane if the pilot can see 123 kilometers. So if you would please pause the video and give the children time to set this up and try it on their own. Let's do that now. Pause the video. So the pilot can see 123 kilometers. I need the radius of the Earth. Since this is already in kilometers, I can just keep the radius of the Earth to be 6375 kilometers. I don't need the 3 zeros because I just want them to be in the same unit. If you do want to change it to meters, fine. This 123,000, this is that big number with 3 zeros on it. But all they have to be is in the same unit. So awesome. Let's find x to do 123 squared plus 6375 squared equals x squared. And I'll punch it in my calculator. 123 squared plus 6375 squared equals that. That's what x squared equals. I want to square root that number and get that. That's what that big old hypotenuse of x is. I need to take away the radius of the Earth from that number. So I will subtract away 6375 and get that. So x is about 1.1 blah blah. This answer right here in kilometers. This is the answer in kilometers. If you go back to the problem, though, many of you probably have 1.2 kilometers. That's not what I wanted. I want the other problem. It says to the nearest meter. So I don't want 1.2 kilometers, and I don't want to round 1.2 kilometers to the nearest meter. I want to round this dirty number, so I need to change it into meters by multiplying it by 1,000, which means just move the decimal 3 places and look at the number to the right of that. If it's 5 or larger, round the 6 up. If it's not, keep the 6 the same. So about 1,186 meters was the answer, if I can get there. X was about 1,186 meters or whatever that number was. Cool. So there it is. That's today's lesson. And this, my friend, was the last geometry lesson ever. Everything else from here on out will be review. So the finish line is close. So how about a round of applause for the last geometry lesson ever? All right. So if you'd please pass out the homework now. And please, please, please come see me if you have questions. I know I haven't been here a lot for you, so I apologize about that. So come on in and see me. Have a good one.